quick introduction about myself. So I'm James, VP of Engineering at Zilliz. I also built Milvus from scratch, like back to 3-4 years ago. So we are kind of like the most scalable, performant VectorDB solution in the market, as well. We are open source. So I before joining Zilliz, I actually worked from a couple of different databases, from Oracle. Then I joined Alibaba Cloud as a like database designer. Okay.
James, can you speak to the mic?
Okay. So get closer. Okay. Yeah. So today my talk will be cover 3 different parts. One is why semantic search is not all you need, especially when you build RAG applications. Second is how we're going to do it, why it is better than like a lot of the existing solutions. Last one, I want to give a quick demo about how you can just write very simple code to implement like RAG with hybrid search. Okay. So, oops. I want to move. Oops. What happens? Okay. So quick recap about like RAG. I'm pretty sure like everybody here should think like ever heard about RAG, right? So it's actually simple. As simple as you can do is just to put everything chunking, put into a VectorDB. Oh, that could be better. Okay, so put everything into a VectorDB, and then like when you want to do queries, you're actually embedding all your queries, search into VectorDB, and then you get some of the like key facts, and you store it on your like large language models. Then you can get a reliable answer, right? Remove some of the hallucinations, right? Sounds to be really simple, and it actually works pretty good. Until one day, when I was trying to build a RAG application by myself, I worked with my friends. What we want to do is actually a legal like applications. We actually have some kind of very special legal terms in the document, right? So when I using this RAG application as well, I just using as like VectorDBs. At first, it looks to be really, really good, but if you take into a deep consideration, you'll see that some of the terms actually are not searching as expected. We actually saw the search becomes like overly broad. So if you search for one term, you may get some similar terms, but there's nothing can control it, right? So I'm trying to start thinking about how we can fix that issue. I actually using 2 solutions. One is just fine-tuning my embedding models, and also large language models. It works okay at the very beginning, but soon I find with more and more corner case, when I start training my, fine-tuning my bad cases, I saw like larger models start to forgetting a lot of like basic informations. The main reason we use larger models or embedding models just like they have been pre-trained with a lot of like existing information, right? So with a lot of fine-tuning, it starts to forgetting, and the score actually, the evaluation score actually goes down, right? So the other way I actually tried is doing query writing. So I'm trying to find all the like synonyms for certain kind of terms. I try to change the way speaking, use larger models to change, like doing a lot of tricks on that. But I soon find there are like just too many corner cases, and you cannot fix it for your use case, right? So there seems to be nothing we can do. Okay. If you look at what is actually wrong for semantic search, right? It's definitely not all you need. It's actually pretty good technology. We build VectorDBs, so I won't say like VectorDB is not good. But they are like lacking of 3 major things, right? One thing is there is no way you can control your result, right? You just like larger models, they're basically just a black box. So why you get this result, why they become similar is all a black box, and there's nothing we can do if things goes wrong, right? Second is that it's failed to handle some uncommon queries, right? So dense embedding models is trained by a large data set, but still actually the data set is coming from the web, or those are very common stuffs, right? But under your use cases, you may find that for some special term or special like queries, it works not pretty good. Sometimes they don't even say the token like in the training data set. So it won't work, right? Third thing is always about chunking. we all know that chunking is not easy. The easiest way you can do is just a chunking by 4K, 8K, but there are a lot of trade-offs between, right? Long chunks, you lose all the context, or you lose all the details. If you're using short chunks, like 512, then you lose some context, right? So it's always the hard part to like how you chunk your data. Okay, so how we think about a way to fix that. So then I started thinking about what makes search very powerful, or what is the like way we can do search. I think it's all about probability, right? So no matter it's large models, no matter it's embedding models, so the only thing they want to do is like trying to find like some patterns in our like documents, in our corpus, right? As easy as it can be, if you like calculate the frequency of English letters, you'll definitely see some letters get higher. For example, E is actually shown much more frequent. So if you want to build a small large model to predict the next word in the document, I will also pick E if I don't have enough training data set, because that makes most sense, right? Same here for 2 gram. So if I put 2 letters together, you definitely see some of the patterns is actually not staying there, such as ZX, JQ, but some of them are very popular, such as TH, right? Okay. So same thing happens here when we put into not only about letters, but if we put into tokens, that's how large model works, or just to predict your next tokens, right? So with enough training data set, then you know what is the highest possibility that could be the next word. And you know which kind of like letters actually, or tokens are actually most similar, right? So the question is, how do I improve the probability, right? One way to do that is always using pre-trained models. OpenAI is definitely pretty good. We also know a couple of like embedding models, Voyage AI, Cohere. They train from like massive amount of data. If you're trying to build a legal data set, they have law models. If you're doing finance data set, they have like models training for those specific data set. And sometimes you can do some fine tuning, but I think those tricks are not like works pretty good on some of the use cases, right? So the other way you can do that is to figure out your own data distribution. And that sounds to be very, very difficult, but that's not that hard, right? Okay. So the way we do that is actually very traditional, but it's actually really helpful. To start from, we need to recap. So those part will be a little bit technical, but hopefully that I can give you a like general background about what's happening there. So the very traditional way we can get these stats is something we call TF-IDF. So TF means term frequency. So it shows how much time each token shows in your corpus, right? So the other one is IDF. It shows that the frequency of each token among all of your documents. So for example, if I have a lot of words in the same documents or in my corpus, which means this token is not going to be very important. It could be a the, it could be a or it could be like very common tokens, and it doesn't contain enough semantics, right? But if you saw some very special words we never saw it before, it only shows once in your corpus, then which means their IDF is going to be only 1 and its width is going to be super high, right? So if you get all your data set, if you do all the stats, calculate all the term frequency, all the inward document frequency, then there's actually a way to calculate the relevance between your query and also your like corpus. That is what we call as a TF-IDF. So Elasticsearch and all like Luan-based like search actually using the same technology, but they definitely different versions of how you can calculate the stats. One of the most popular ones is called BM25. So they generally using the same idea, but they change some of the like hyperparameters to make sure that search makes more sense, right? Okay. So what could happen when you're using TF-IDF? So it's generally 3 different steps. The raw text here is Milvus, the vector database built for scale. First part is you have to split into different tokens, just as large language model do. You have different tokenizers. Sometimes the easiest way is just split by like 4 letters, 5 letters. But you also can use a lot of different like stop word, using a comma to split everything. for sure we have some integrated solution for that, so you don't really need to worry about how to tokenize. So after you tokenize, you do some transform, make sure that you do lowercase, you do stammer, you remove some of the very common words. So now you get some clean tokens, right? With those tokens, second step is you actually have to build an inverted index on top of it. So I'll show what is an inverted index, but it gives you some like performance when you try to search on those, right? Third part, you need to stats. That's how we figure out our data distribution. So the important part is that we need to calculate, for example, how many times Mills shows in my document, how many times vector shows in my document, right? Ideally, vector should be like shows more compared to Mills and the other, because vector is like more like a common words, right? So which means if Mills shows it, it's actually going to be more important than vectors because it shows that in all the documents. Okay. So I can give a quick example about what happens. So I have 3 documents. One is the information retrieval is a field of study. Second, the information retrieval focus on finding relevant informations, whatever. Third is that data mining and information retrieval overlap in research. Okay, so those are 3 documents I have. If I search for information retrieval research, which one should be more important? Yeah, I think ideally definitely number 3. First of all, because all the 3 tokens I have, information retrieval research actually shows in document 3, right? And what about document 1 and 2? Which one is going to be more relevant? Yeah, the answer is document 1 is going to be more relevant because document 2, they both have information retrieval as a keywords, so it's all there. Information actually shows much more times, so it has less weight. Retrieval shows like less time. It's only 10% of your document has retrieval, so it's become more important. And after you do all the calculation, and sometimes you also need to divide it by the length of your document to do some kind of normalizations, and you can also like always calculate the scores, right? So that's a normal way how we using BM25 to evaluate how query and document are relevant. Okay. So it sounds to be really good, right? So we know we have a way to control it. We just need to know about the tokens. Everyone can read the tokens. We can modify on that. We can do filter on that. Is that good? The answer is not, it's not enough, right? So that's why we still need VectorDB. Reason is, first of all, sometimes you lose your context. By just doing semantic search, by just doing lexical search, you're just trying to find most similar words. But sometimes, for example, the apple words, they have multiple different meanings. Do I mean the fruit apple? Do I mean the fruit complaint? Yeah, so that's going to be one challenge. VectorDB or vector embeddings definitely help to understand the thing, like behind the scene, right? So the second thing is, what about the synonyms? So sometimes, even if they have similar letters, similar words, they have like different meanings. But on the other side, even if you have totally different words, they might have similar meanings. That's why VectorDB or vector embedding still going to be your very important for a use case. Third is about your intentions. Just by looking at the word change criteria, if I have different contexts, if I'm looking at the e-commerce website, or if you're looking at the car manufacturer website, I actually searching for different things, right? So it's not, so just using like keywords or just using lexical-based search won't help a lot of these use cases. Okay. So that's what we propose in Milvus 2.5, which is a new hybrid search model, combining both lexical search and semantic search. So first of all, it works pretty good if you look at the numbers here. So by just doing dense or sparse, you can probably get 50%, 60% of your recall at most. But if you combine all those and you do a re-ranking, definitely shows a lot of like improve on your search qualities, right? So we actually using a model called BGM3, so it can generate multiple different embeddings. And BM25 is kind of like the same. You can combine both BM25 and also a pre-trained model together to get a better result. Okay. So what's the challenge here? So if it's already so good, why it's not like put into production, right? So a couple of things is actually the blocker to put hybrid search into production. One is it actually makes your architecture more complex. So this is a very common architecture. For Elasticsearch, a lot of people using Elasticsearch, using OpenSearch, using Sola, and they are not pretty good at like dense embedding search for performance, for cost. So that's why you also need a special vector DB, which is your email. So I know there are like some others, but generally what you do is build a system. You have a search service. It helps you to do ranking, help you to store all the raw data. But you also need a system for lexical search and system for semantic search. And you also need your embedding models, right? So that makes your system become very, very complicated and there's no way to maintain it, right? Second is with multiple different embeddings, so also like say cost issues, right? So you see like you have to double your cost, sometimes it's like even triple your cost because you maintain multiple different embeddings, right? And also you have multiple different like bottlenecks, right, on your performance. So it's very hard to diagnose, it's very hard for observability. Okay, so that's why we start to think about like merging into one large cluster or one like database can host both like vector search and sparse search, right? So this part is gonna be a little bit technical. So it gives a little bit background about what is a traditional Elasticsearch engine or what is the ES do. So generally speaking, what they do is they're using an inverted index. So for each of the token, they actually like list how many of the documents actually contains this token, right? For example, if I have like a Harry Potter book, I split it into different chunks, and Harry is going to be my token. And for different chunks, token 1 has Harry, token 2 maybe have Harry twice. So that is how I made this inverted index list, right? So when search happens, the easiest way we do is called DAT, short for document at a time. So we just quickly go through all the, for example, when I search for BCA, in my use case, BCA are just different tokens. So I start from B, I say, okay, D1 is actually related. So I go to C, D1 is related as well. So I add up all the score here. And A is also related to D1, right? So D1 get a score of 2.5. That's a relevancy. So the 1 is actually the BM score relevancy we talk about, right? So then we go to the next document for D2, then D3, it goes one by one. And you see that if your inverted list is gonna be long, it takes you a lot of time to like go through all the lists, right? That's why the performance is not really good. Okay, so there's definitely some smart way to improve on that. So I won't talk about those details, but remember there's actually called weekend or WN. So the overall goal for this algorithm is just to skip some of the tokens or skip some of the documents. For example, if I already find one very relevant document, the easiest way we can do is we can skip all the documents which don't have enough weights. So you don't really need to understand that, but under that case, you'll see that D2 is actually, the score is actually much, much smaller than D1. So we skip it and directly goes to D5. So if you guys are interested, there is actually a very good paper about this. This is a very like basic paper for all the like search. So I would recommend you to read more about this in the paper. Okay. But is there any like drawbacks for WN? Definitely there is. Otherwise, we won't build it in Milvus. I think it's hitting to a lot of performance issue on many of the use cases. If you have large top K, you have large chunk size, you have a lot of long queries, but that could be the case in building RAG applications. If you think about traditional search, usually people just keep searching like 3-4 different keywords. But on the RAG use cases, usually a query is going to be long because everyone's talking about you need to give more context for your large language models, right? So people turns out to write longer prompt, right? So search becomes more like performance intensive, okay? So that's why in Milvus 2.5, what we built is something called a hybrid index, right? So it's a little bit different from traditional index. The two major differences, first of all, we have multiple different index implementations. Instead of just using inverted index, we also have a graph index. if you guys are familiar with VectorDB, that is what we do for dense embedding as well. Graph-based index is actually pretty good when you have long context, when you have large top case. And the better part for graph index is you can utilize a lot of machine learning things. For example, you can do quantization on top of it. You can do a lot of hardware acceleration on top of it. We use SIMD. Also, they actually rating in C++. So the performance is actually much better. So, sorry, the graph is a little bit small. But just to give you a very quick idea, so we did some tests on many of the data set, and the results say that almost on the similar recall compared to ES, memory usage for Milvus it's twice less compared to ES, and the performance is usually 2 or 3 times faster. That's simple because we utilize a different quantization policy, so the recall going to be lower a little bit, but you see high performance growth and also more memory saving. Okay. So the background seems to be really, sometimes it's gonna be hard to understand if you don't have the background, but don't worry about this, right? As a user, usage is gonna be very simple. So it's just gonna take 3 steps. First step is create your collection or your schema information. So from the code here, you need to actually specify a function, help you to do all the embeddings. Here we have BM25 functions, right? So you actually specified the input field as actually tags, and the output field is sparse, okay? And using the BM25 to do all the embeddings, right? So that's the first step. You have a collection. Second step is you have to build an index on top of it. So the index we're actually trying to build is the inverted index. We also have the graph index version, right? It's a bunch of parameters. You really don't need to worry about it. And third step is you need to insert your data. So your data is just beyond pure text without any embeddings. That's a major difference between Milvus 2.5 and all the previous versions. So for previous versions, it's almost vector in, vector out. So you have to do all the embedding generation by yourself. But right now with all the functions, it can help you to do all the embedding generation. So you only need to offer the full text. Right, so we're also working on the dense embedding part. So we try to integrate a lot of different embedding models and re-ranking models. So using vector database is going to be much easier. So you don't really need to worry about how you handle embeddings, right? So after data is actually going to insert, you just search with another string, who started Elasticsearch. Yeah, so as that easy, you actually do the very basic demo for sparse embeddings. And you can also work sparse embedding together with dense embeddings for better performance. Okay. So we're just going to release this Milvus 2.5 version. So just next week. So this is the first time I talk about all the new features here. So feel free to talk to us. This version will be very focused on having more search functionalities. So not only for BM25, but we also have keyword matching. So for a very long context, if you want to filter out one of the document with keyword Milvus, that is actually doable. We have multiple different indexes to improve the filtering performance. We also add a lot of different quantization, help users to reduce their cost when they try to do vector search, right? So right now we'll be preparing for Milvus 3.0. So we would also like to hear about your feedbacks. So in the new version, which is targeting on the early next year, we also have interesting features like UDF, hard code data separation. I know a lot of people trying to do multi-tenancy. We actually have a talk about multi-tenancy. So one of the key challenge here is how to save the cost for a lot of code tenant. So that is one of our goal for 3.0. Yeah, but feel free to grab me, give me more feedbacks about what is the feature you actually need. So we keep improving Milvus for a lot of AI applications, right? So yeah, so one quick thing about who we are. So in case you don't know Milvus, so we kind of the most widely adopted VectorDB on GitHub, open source for sure, under Linux Foundation umbrella. So we have more than 400 contributors, over 30K stars. Yeah, we move very, very fast, and over 1,000 enterprise companies actually using Milvus as their VectorDB. Yeah. So if you have any questions about us, feel free to contact me. All right, thanks.